Yes.
All right. Good afternoon, everyone. We are about to start with the last session of the day. These are kind of deep technical talks, quite a few of them. So I hope you still have energy. You had your last bit of caffeine. And first of it will be Stefania talking about the work on reliable property graphs.
Yes, so first of all, thank you, Gabor, for inviting me. So this is the first time I attend in person. A bit of a different talk from everything you've heard up to now, so I hope I don't bore you too much. So the point is there are many graph database applications, and it's kind of folklore by now that they're used in many critical domains, in healthcare, in finance, transportation, cybersecurity, and that these leverage rich graph data models, in particular, the labeled property graph model that you know, so directed attributed multigraphs that can also be multi-labeled. You see here an example. And in particular, in the recent years, we've also defined constraints languages on them. In particular, I was involved in the PG keys working group within the LDBC. And as a community, we propose this language that allows to uniquely identify and reference property graph objects. And these constraints have two components. So we have a scope in red that serves to basically define a unique single object that we want to constrain. And then we have the descriptor, so the second part in green that describes the key values. And then we have three types of qualifiers. So exclusive that says that no two objects in scope share a key value. Mandatory that says that each object in scope has at least one value. Singleton at most one value. So we also have combinations of these qualifiers. Exclusive mandatory provides referencing, and if all three are satisfied, we have identifier. And just to give a small example on the schema of transportation graph that comes from a real-world application, we can, for example, say that each stop, so a node in the graph, is identified by the value of a particular property. Here is called stop ID. But we can also say more complex things. So in the scope, we can have more complex queries. For example, I can say that each route that I can compute with the graph query that filters only those that have been used in a trip is identified by, for example, the value of its short name and the agency that operates it. So this is an example where we have a more complex graph query in the scope part of the key. And to validate these PG keys, well, we can implement them on top of any graph database system. And the nice thing is to validate it, we can run graph queries. So in particular here, if I want to say that routes are not shared by agency and each agency operates at least one route, I would have this exclusive mandatory constraint that I can just validate by checking that these two queries return empty. So no two agency operated to the same route, and every agency operates at least one route. Okay, and what can we do more? Well, we can also have cardinality constraints. Basically, the qualifier can have a count, lower and upper bounds. And if we put all of this and we include typing of the property graph, we have a property graph schema. I'm omitting a lot of more complex features, in particular of the typing and of the enforcing of such a property graph schema. And this allows us to construct a graph type and basically characterize the structural, so typing content of the graph and the constraints on it. Again, key constraints, cardinality constraints. So this is what has been happening very recently. What happens in practice when we have applications? So already graph database vendors have not integrated yet such complex graph constraints. In Neo4j, we can have key constraints over properties of nodes, but to the best of my knowledge, not over edges, and certainly not constraints as complex as PG keys. Janus graph, for example, does support more complex cardinality constraints, but in general, yes, PG keys and PG schema are largely not supported in the complex manner in which they have been defined. But what happens really with applications? Like even if graph database management systems cannot allow expressing these constraints, do the applications somehow need them? Is there some non-trivial way in which applications leverage schema and constraints from the graph? So this is one topic that really bugged me in the past year. So then I was looking into open source graph database applications that leverage graph data non-trivially, so not just through querying. And I was specifically looking at the logic of these applications, which is non-trivial. And what we can see is, for example, with this transportation application that wants to predict what new accessibility routes should be set in place to improve transit in certain areas, we see here that we have a branching condition that depends, for example, on edge labels. And later on, a branching that depends on cardinalities over the graph. In another application, analyzing citation networks, we see that the output relies on schema constraints. So specifically, certain property values not being there or being not incomplete. So this brought about the question, how can we enforce the reliability of graph database application in the presence of constraints, right? And there are two things that are challenging. So first of all, one needs to be able to produce valid input property graph test cases to ensure compliance with the application constraints. And then second of all, we want to be effective when it comes to testing. So we want to maximize the coverage of the application logic and the branching paths that we have. So what is the state of the art? So there's extensive work on testing, but particularly on graph database applications, there has been a gap, right, in the literature. So there's a lot of work on testing database systems, graph database systems, but not applications. For applications, work on relational, but not specifically on graph. And while there are grammar-based fuzzers that help with testing API behavior, and there are synthetic graph generators, no work has looked into how we can also ensure the effectiveness of these property graph test inputs that we want to feed to our testing tool. So the main motivation is in the graph database application setting, the behavior depends on both the structure and the content of the input graph instance, and we want to detect real bugs that are due to unexpected graph instances or violated constraints. So to do so, we want to be able to both have property graphs that satisfy PG types, yeah, and more complex PG constraints. So one concept we'll be leveraging to improve this branch coverage is the fact that whenever we have a branching condition, so we want to be able to maximize the number of paths that we are able to exercise. So the key idea that we're going to use with this graph database application fuzzing is that we're going to repeatedly run the application on different inputs. We're going to record the coverage, and the inputs that generate new coverage are going to be mutated because they are interesting. Then they're going to be refed into what is called a fuzzing loop. And we're going to continue this with the aim of traversing as much of the application as possible and covering every execution branch and finding errors while we do so. So this, in general, is known as fuzzing, and they are typically black box testing approaches that are code agnostic, but that might miss rare behaviors. There are white box testing approaches that have access to the entire code, but they are very computationally expensive. And what we're going to do is we're going to design a gray box testing approach where we're going to be guided by this additional coverage feedback that I have mentioned. And with this in mind, so the specific purpose is to design a gray box fuzzer for graph database applications that support graph constraints. So we have this tool called PGFuzz. So it has three parts. So the first part is the instrumentation part that allows us to record this coverage feedback. Then we have a part that produces the graph seeds that we pass on to the application. And then we have another part that takes care of the fuzzing loop that I mentioned before. So selected inputs and mutating the inputs. So the instrumentation part, basically we did it by having our own API where we abstract mainstream operations, so CRUD operations on graphs, and we will redirect the calls to the application to instead our API and track this code coverage. And this allows us to be more efficient when running our testing. The more interesting part is now the fuzzing loop. So in the fuzzing loop, we need to mutate these test inputs that are interesting. So a base strategy for mutation is at the level of individual bits or bytes. So what we do is we look at the byte representation of the graph, and basically we can flip bits or bytes, insert them, delete them, and try to see if this produces any crashes. But the problem with this approach, which is very basic, is that in practice, 90% of these actually corrupt the graph structure, and the remaining mutations that do not corrupt the graph structure only impact property values, but not in a non-trivial way the structure of the graph. So this led us to want to be able to apply transformations, really graph transformations to the graph inputs to obtain more interesting test cases, and in particular to obtain those that lead to semantic constraint violations, so key and cardinality in particular. So what we did is we categorize the different types of constraints that we want to stress test. And for each of these categories, we define specific mutations, so transformations, that we then apply. So for example, if we have cardinality constraints like simple many-to-one or one-to-many, then we produce graph inputs that explicitly break this. And when we wanted to evaluate, so we built on top of JQF that enables already coverage-guided fuzzing in Java applications. And we used as baseline synthetic graph generators, mainly GMARC, that already allows to produce valid graphs, but like I said before, does not take into account the coverage aspect. So what were actually the applications on which we evaluated our tool? So this is the more problematic part, is that we looked at open source graph database applications that we could use, and there were not that many that were leveraging these constraints in non-trivial ways. So we built our first benchmark. We have 9 of these. Most of them are on Neo4j, some are on Janos graph, and you see here the characteristic that they have. But it would be really interesting if we could build more benchmarks that highlight the need for such constraints that are already being proposed in the literature, and that would be really useful to develop these testing tools. And when it comes to evaluation against the baseline, so we were able to have much higher coverage than the baseline. But interestingly, not all the benchmarks were covered at 100%, because of course there were parts of the code that maybe were unreachable due to previous filtering conditions, or because of the fact that the input depended on very rare graph patterns, or inputs that were very unlikely, like sequential property IDs. And we were able to catch some bugs, mostly number format exception, null pointer exceptions, or array index out of bounds, mostly coming from these unexpected graph instances. And then we analyzed, to what extent each of these categories contributed to each of these bugs. And null pointer exceptions were caused by removing or changing graph elements, breaking these constraints, and array index out of bounds could be caused by any of the transformations that we defined. And then we also tried compounding transformations, so applying multiple changes at once, such that we create more complex graph structures without removing subgraphs. But the problem is, because of the fact that our applications benchmarks were not very complex in the semantic constraints that they were enforcing, we did not report any significant improvement. So it'd be very interesting to have applications in which some pattern-based branching condition depends on more complex structural motifs in the graph. So yeah, this is our tool, and it's open source, and you could use it. And it's the very first attempt to really test these graph database applications. And then I asked myself, okay, what happens in the distributed setting? So in the distributed setting, obviously things are more complicated because we have to either partition the graph, in which case updates are easier because we only update one replica, and we know where we do the updates. But of course, the traversals are more complex. We want to minimize the cross traversals, and this is expensive to compute. Or we can replicate the entire graph. So then the graph traversals are easy, but the updates are hard, right? And we're going to talk about this. And of course, in the distributed setting, we have these synchronization mechanisms. So all replicas have to agree, or most of them have to agree, or we have a leader-follower approach where one replica takes the updates and the other ones replicate it. So in the literature, we have native, non-native systems. Some are partitions, some are replicated. Some utilize consensus, quorum, leader-follower. The ecosystem is very complex. But what happens specifically, what are the challenges, the research challenges that appear when we take into account these constraints in the distributed setting? Yeah. So let's look at PG keys. Let's say we have like a simple graph with doctors and departments, and let's say that we want to enforce the constraint that each department has a unique manager. So then the Paris replica adds an edge, and the Rotterdam replica adds an edge. And then let's say that they merge the updates in the Delhi replica. So even if locally none of these replicas actually violates the constraints, later on when they merge the states, the constraint is broken. Yeah. So how can we allow for replication of graph data with this constraint preservation in mind? Yeah. So there are approaches that have been proposed. In particular, there are replicated data structures that we could leverage to build property graph replicated types. But when we add the extra element of constraint satisfaction, things become more complicated. So in a recent vision paper, we analyzed what happens with various workloads under varying consistency criterion. So here in the upper part, we range from eventual consistency to strong serializability, depending on the amount of coordination that we allow. Yeah, so in the eventual consistency setting, we do not have minimal coordination, and in strict serializability, we have very strong coordination. So what happens with the different workloads? So in the OLTP setting, we can have these reads even with minimal coordination and the eventual consistency. So it can be very highly available if we are allowed for some degree of staleness. Yeah, but as soon as we go to cases where we have writes, yeah, we would need TCC, so transactional causal consistency. And in particular, when we have graph traversals, this is also needed. So TCC in practice, it's the consistency level that enforces the strongest consistency while allowing for availability. Yeah, and the most complicated situation appears when we want to do graph analytics, because there we really need strong consistency. So typically we require either SI or SSCR, yeah, strong serializability. So this was a high-level analysis. So now we're working on more formal proofs and impossibility results, and really a more fine-grained analysis of what is possible, yeah, under these different scenarios. And particularly here, an interesting question is, somewhere here, is there some consistency level that maybe would be interesting to define specifically for graphs? Yeah. So there have been some proposal, Jim Weber reciprocal consistency 5 years ago. Is this still the case? Can we do better? What are the options? And under those consistency requirements, what kind of workloads could we support? And specifically when it comes to graph constraints, yeah, as you see, again, we did this analysis on PG keys and PG schema where we combined the typing with the key constraints and cardinalities. And if we really want to uphold such strong invariance as PG schema in its full power gives us, we really need a strong serializability. But in between, there's a full spectrum to explore. Yeah, and the vision here is doing this in a principled fashion, so that indeed we can have this replication in a reliable manner, and then that we can also have tools, yeah, that help us validate it. So yeah, this is a bit of a tour de force on basically 2 papers. So the first one was in ICGT Graph Transformation Conference this year, and the second one a vision paper at PAPOC. But basically are these 2 themes of reliability tools for property graph applications and taking into account this aspect of scalability. So to conclude a bit, yeah, we see that there are tools that can be adapted to the property graph setting, but they would need to be accompanied by suitable benchmarks. So in particular, it'd be really nice to have benchmarks of applications, toy applications, micro benchmarks that we could extract maybe from real world, more complex settings that could support the development of such tools. And when we scale out these graphs, how can we support these semantic constraints with minimal coordination in an efficient and reliable manner? And then here there's a lot of work to be done, like I said, on these data structures, synchronization algorithms, and special techniques for ensuring reliability. Yeah. So now I'm open to questions and further discussion.
Thank you.
Why does PG types, basically conformance, what you've got under the aegis of PG schema, require global total order? It seems to me that these are sort of orthogonal concerns. I mean, I could partly apply a number of and a disordered way, a number of schema valid updates to a database, and it wouldn't, if they're sufficiently narrow in their scope, it wouldn't actually require global order.
Just the typing. Just the typing does not require this. But here, when I say PG schema, is the most. I mean PG schema on steroids. I mean where I combine everything.
But you separated out PG keys.
Yeah, I separate out PG
So
keys.
if we go back to the other slide.
Yeah. So typing, just the typing can be locally enforced. That's not the problem. The problem is with the keys and with the cardinality. And then for me, PG schema is everything. Yeah.
What does PG schema versus PG key constraints mean? Because either PG schema contains.
Yeah, PG schema contains PG keys and cardinality.
That's what you mean by.
Yeah, that's what I mean by it. Yeah.
And you're not making a statement about the types.
No, because the types can be locally preserved. So that's not the problem.
We would say PG schema, then we would say types, then we would say.
Yeah, I would say this.
Yeah, no, that's fine.
It's just like when I presented it here, I put them all 3 together. You see, like so the PG schema is the types, the keys, and the cardinality.
That's understood.
So typing is locally maintainable. It's not a problem. Keys are complicated if they have graph traversals. So we need TCC, and cardinality is complicated. We need SI or SSR, because when we have these aggregates.
Right. But actually, I think that if types are more complicated, if they become subgraph types.
Yes.
What is actually going?
Yes.
Kind of what's going on here. And my other question was, doesn't PG keys have an effectively arbitrary constraint that it only goes up to parts in terms of the actual complexity of the subgraph that you can apply a constraint to? My recollection was it didn't go as far as you presented it, where there is, if you take your diagram where there's a red subgraph and there's a green subgraph.
Oh, sorry, yes.
Right at the
Yeah, I also consider this extent because I try.
I think that's an extension of what it actually
Yeah.
says.
So in the scope of the PGT, we have, so if you have a unary query, only one thing. And here in the descriptor, we can have a more complex graph query. Yeah, but here it's unary, yeah?
Right.
This is the only thing.
Yeah.
And then what does happen is in the PGKeys paper, sorry that I'm going like this. So in the PGKeys paper, when we were actually looking at, the scope, we define it on nodes, on edges, but we have this extended part where we can also define it on paths.
Right,
And then
up
it's
to
really,
path,
yeah,
not
yeah.
to another.
Yeah. But we could, of course, extend to RPQs and combinations thereof, and then it becomes really complicated to do the analysis. That's why it's a vision paper. So the vision is to really have a pen and proof version of this table with the fine-grained analysis of what is possible under what consistency level. And again, the question is, do we need something special for graphs in terms of the consistency we should uphold? Yeah, and I would like to really, stress this benchmarks needed, because I was really surprised that like I couldn't find any interesting applications that are open source and that leverage this schema information in a non-trivial way. And so if we could do this, if any people working in industry do have such applications and would want to extract a micro benchmark, it would be really helpful. Yeah.
Yeah, amen to that. Please.
So I'm just a simple person standing in front of a crowd of industry people, asking them to give me micro benchmarks.
Excellent. Thanks.
Thank you very much.
Next up is Amin. Let's see. Do you need speaker notes?
Sure, just so that I see what's coming up.